So, past few days, I started doing mathematics again, particularly the discrete mathematics part. And over there, I stumble upon what we call as bipartite graphs. We're not going to the coding part, but we are trying to discuss it because during my bachelor's, I think I didn't went into that much of depth into this bipartite graph, but my more of my attention went towards the RB trees, the red black trees, and the AVLs, and particularly other one was could be the heaps, not the memory one, but the trees, a heap tree, heap sorting algorithm, all those things. But more attention went towards the RB trees. So I started looking more into this bipartite graph. I came across towards it while reading the again doing the optimization thing. So I never been able to look into this. So I thought like why not look a little bit more into this graph, this bipartite graph. The basic idea is that we are having a set, a complete set, but basically we're having two disjoint sets. Okay, so these are the two disjoint sets, and they could be like, for example, they could be like the mating decision. Let's try to look from that perspective. I think we're going to end up on that example soon, but you can think of that as a collection of males, and then there is a collection of females. And the major property that bipartite graph has, that these connections are disjoint. So disjoint means that they're not going to having, how could I explain it more? Disjoint means they're being like cut off. You can think of like they or have no connection previously. If I'm being wrong, like just please correct me. And they're not going to have a relationship on themselves. For example, if I in today's time, I think could be a little crazy in 21st century. I don't know, but if we started looking from evolutionary biology perspective, I think that it's usually from males to females and females to males. It's I don't know, man. Maybe it could be someone today might have some sort of relationship with themselves. Quite common today. I'm not gonna comment on that. But if we started looking at these two examples right here, that males have a certain, you know, weights or sort of a properties that females desire, and that females are there which they might have certain properties which males desire. So it's like these two subsets here, and what we wanted to do is we wanted to make as efficient connection as possible, which means that we want to make sure that more and more males are happy as well as more and more females are happy, so everyone is happy. So that's what our goal is, and that's what problem this bipartite graph is actually solving, is uh, optimizing this process of decision making basically. Well, graphs usually used in decision making part, in coming up with better decision, be it like for example, usually we have a graph idea regarding with traveling to alternate city or to a certain distance, and over there what we do is we started looking at maybe some a better route which could be like having less sort of a traffic, and there could be another route which is making sure that you're going to end up with the shortest path, you're going to take the less time. So it depends on the situation that what we exactly want. Again, it is solving the same problem of optimization and making us everyone happy. So that's what graphs usually do, and that's exactly how I used to started thinking about graphs in the form of subsets. So once you started thinking about graphs into subsets, that actually started making more sense, because now as soon as say subset of cities, now you be like, okay, so I have traveled to where, in my hometown, then there is close by New Delhi, then I might also have went to Nainital. So these three are there in that subset, and I can find a path in between them. So that is a pretty good way of looking towards the graph, instead of just node and edges, but towards the subset. So what bipartite graphs are doing is you started to make, for example, if there are like n sort of males, and there are like m number of males, and I'm just representative here. I'm not going about into more of that part, like just leave it. So n number of males are there. Let's take, this is an arbitrary numbers. There could be like anything. It could be like 10,000, maybe 1,000 males, anything, and maybe 1,000 and 10,000 females. It again depends the number of the males and females. So you want to make the connection between all of them. You want to make sure that who wants whom, and that is something is a problematic, because once you started doing these, like between, let's stick that there are n number of females and n number of males, for example, right now, instead of n and m or m and n, stick n and n. Okay, n n. Okay, so you started having these connections between n number of females, n number of males, and once you started doing manually, you're gonna end up like up to like it's gonna be a lot, because it's like, how about like 2 to the n somewhere, I think. Yeah, it's like 2 to the n, because you're like having 2 and you're making n sort of connections in between each of them. For example, you have just, for example, you yourself take the example that you wanna match up with n number of people, and that's like, that's a big, it's a humongous size of a number, so we don't want to do that. So we want to improvise, or we want to improve over this, and we want to do something better. So how about doing, like, how can we eliminate certain steps? I think we can do. And is that somewhere we started doing an optimization sort of a thing. It's not a certain algorithm, but it's like a it's like a very precise approach which we are taking, like a sort of a probabilistic way of thinking, or maybe matching these connections. So what are we doing eventually is we started looking at, hey, this particular male is there, and this has this particular characteristics, or maybe this belongs to this particular species. So why not eliminate all the species which is not, which does not belongs to him? So this males, for example, belongs to lions, and so, and there could be like another zillions of species there. So you could eliminate all of those and just start dealing with these lines, and that makes more sense, isn't it? So that's like a pretty starting point of taking the optimization in with bipartite graphs, with these two disjoints right here. So you are doing what, trying to eliminate certain steps. So like, okay, but what if this particular line just not belongs to this lines kind of a region with, for example, n prime of these lines, n prime number of lines, let's take this n prime, and instead of having n prime, these lines also have an hierarchy. Now there is a problem, because you haven't think about that, and you try to optimize, which is like, which is way better than which is way better than a Java programmer. I don't know why I just came up with, but I think we're doing much better than a Java programmer. Sorry if anyone like got upset with that, but we got n prime number of lines, and n prime number of females are also there, or maybe some less females are there. Now the competition is much higher, which is like a challenge now, because now males are having some sort of hierarchy based on their maybe features like hairs, the amount of kills that they take, the amount of males that they have defeated. So there are various factors started getting integrated into this just particular this line set. I'm not even talking about the other males over there. It could be humans, so humans have social hierarchies. So someone is earning more, it's more desirable by females. Female is earning more, she's not gonna mate below that. So you started seeing these sort of challenges, these sort of constraints, if I say, on these. So how would you resolve it? So there is something called as Hungarian method, or Hungarian algorithm, you can say. You can search about it, you can find the name. I'm not going into that. So what you started to doing here is you started considering the weights, and on based on those weights, for example, this male has particularly 10 of weight and other have quite less. So you started looking at which female has somewhere close to 10. Maybe a female had 8 or maybe 11, so that could be a much better match. So you started matching only those paths instead of having taking these n prime paths. So I think it started making sense to you. Instead of taking these now n primes, of which we already have eliminated, like n minus n prime number of paths. I think I'm not getting into more of a mathematical language, but you got the idea that we have eliminated these much of chunk, and we only left with this chunk, and now we only left with this chunk, and that is way better than again with a Java program. Okay, so we're doing much better than a Java programmer. So we are optimizing it quite well. So now, no, no, just we got certain factors involved. We got an idea that okay, so these lines are going to have certain weights, certain desirable factors. But what if, what if? Now here's the challenge. What if this female has a preference? Hmm. What if this female has a preference? How about that? What? I mean, if she said like she don't want to go with this 10 out of 10 line, she want to go with a maybe a 6 because 6 might have tricked her. Hey, it's evolutionary biology. If anything works out with meeting, like it's a successful strategy. But okay, so fine. So this female now has a preference that she wants a 7 or a 6 line on a rating scale, and again the males over here also started having preferences, not just female, because it's like this altogether we started, evolution has made transfer certain behaviors in males, also in human males. They become quite maternal, they contribute to the family, but just leave it for some other the discussion. But you started seeing that they started having some sort of a preference, and now there is a challenge, not just the weight. Now you also have to consider the preference, which is way more important, because once you're dealing, for example, let's take the example of railway ticket reservation systems. This is the same thing. There is no difference. It's a preference and the weights. For example, the weight could be which sort of a particular which sort of a particular class you're booking for. It could be like third class EC, second class, or first class EC. Could be a general, not journal, general. It's nighttime. Started having problem with words. General coach could be any sort of class that you want to travel, and now you have this thing. Now you got the weights. That's the weights. You started having some sort of preference, which is could be you want an aisle seat, or you want a window seat, or sorry for my eyes, like I'm recording from the very first time from the front camera. Actually its camera is on this side, so no problem. Aisle seat, window seat, could be the medium seat, upper berth, lower berth, anything. You have to consider that. Got it? So there you cannot do with Hungarian method because it doesn't consider preferences. It only considers the weights, the factors which contribute to this particular value to be a little bit higher or lower. Again, depends. So for that, there is a certain algorithm called stable marriage algorithm, or stable matching algorithm method, stable matching method, stable marriage method, anything you want to say. So what it is doing alongside these weights, it's also considering the preferences. And usually males are going to like you can think of a dance party where males are there, females are there, and it's like a prom. So on the prom, well, actually I've never been to any sort of these sort of events, I just avoid that. But in prom usually males have a preference that I want to go with this girl, I want to dance with her. Girls also have, females also have sort of a preference which means that they want to dance with and want to engage. So you started matching them one by one. Then again on next iteration, since who have been successfully been matched, you take out those people, and you the remaining one again went to this iteration until and unless no one's left. If someone's like that would be sad, but again you got the idea. So this is somewhere, I think it's 15 minutes. Okay, so it's close to 15 minutes. And let's try to end this. I don't know, I just don't want to make it much more longer. But I think got the idea that what bipartite graphs are actually doing, they're doing the same thing, but it's a way of representation that you try to create two disjoint sets Disjoint means they're not having any sort of connection in between them already. You try to form some sort of connections. For example, these are like n number of males and females, and you try to the first iteration of the optimization, the heuristically is gonna be like trying to removing these n number of n minus n prime number of these values. Let's try to represent it with p. So you eliminated p number of connections, and you will like have like, okay, so fine, this guy could stuck with these number of females quite easily, so I don't have to look all of these. I can like eliminate completely. It make my work much better than a Java programmer. Oh god. Okay, so you started having these sort of connections, like fine, but now there are weights introduced, so you started matching with weights with Hungarian method, like working fine. But now you started having preference. Females usually have more of a preference than males, and now there is a problem. You want to make as much as people happy, as much as loins happy, whatever man, who cares? But you want to make sure that it is highly optimized according to the constraints, according to the problem, and that's where stable marriage method, and there are like few other methods. I haven't looked into that, look into those yet, but I think you got the idea. And that's what bipartite graphs are. That's what they are used for. Bye.